The morning of August 15th, 1945. Kubinka Proving Ground, 63 kilometers west of Moscow. Soviet engineers gathered around a massive steel behemoth that had been transported over 1,200 kilometers from the battlefields of East Prussia. Tiger II, number 2, 80093, captured intact near Sandomierz in January 1945, sat under the grey Russian sky awaiting systematic examination. This was not merely another captured German tank. This was Germany's final answer to Soviet armour superiority, a 70-ton fortress mounting the most powerful tank gun in operational service, protected by armour that German propaganda claimed could withstand any Allied weapon. The Soviet Technical Commission had tested dozens of captured German vehicles throughout the war. They had examined Panzer IEs from Stalingrad, Panthers from Kursk, Tiger Is from multiple fronts. Each examination followed rigorous protocols established by the Red Army's main auto-armoured directorate. Each test generated detailed reports filed with the People's Commissariat of Defense. The engineers approaching this Tiger II expected to find the same meticulous German craftsmanship that had characterized earlier captures. What they discovered instead would fundamentally alter Soviet understanding of German industrial capacity in the war's final year. Senior Engineer Lieutenant Colonel Mikhail Svirin led the technical examination team. His credentials were impeccable. Graduated from the Leningrad Military Mechanical Institute in 1933, spent a decade analyzing foreign armor designs, personally examined the Tiger I captured at Leningrad in 1943. Svirin understood German engineering philosophy intimately. He had studied the careful tolerances, the precise welds, the attention to metallurgical detail that characterized German armor production through 1943. The Tiger II before him should have represented the pinnacle of that tradition. Instead, it would reveal how catastrophically German industrial capacity had collapsed under combined pressure of Allied bombing, material shortages, and desperate production demands. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Soviet testing protocol began with external examination. Engineers measured armor thickness at multiple points using calipers and ultrasonic gauges. They photographed every surface from multiple angles. They documented paint schemes, markings, modifications, battle damage. The Tiger II chassis, 280093, showed minimal combat damage. A few small caliber strikes on the turret, some track wear, minor mechanical issues that had caused its abandonment. The crew had attempted demolition before fleeing, placing charges in the fighting compartment, but American forces advancing rapidly through the area had captured the tank before complete destruction occurred. Soviet recovery teams found it outside Sandomierz, partially disabled but structurally intact. The first anomaly appeared during armor thickness verification. German technical documentation captured alongside the tank-specified frontal turret armor of 180 mm. Soviet measurements confirmed this thickness. Hull front armor specifications called for 150 mm sloped at 50 degrees. Again, measurements verified thickness compliance. But thickness alone did not determine armor effectiveness. The quality of the steel, the integrity of the welds, the absence of internal defects, these factors mattered equally. Soviet metallurgists took samples from multiple locations for laboratory analysis. What they found troubled them immediately. The armor plate composition showed significant variations from earlier German armor samples. Nickel content, essential for armor toughness and resistance to cracking, measured between 0.6 and 1.2%, depending on location. Earlier Tiger I armor, captured in 1943, contained 2.5 to 3% nickel consistently. Molybdenum, critical for high-temperature strength and resistance to stress fractures, was nearly absent in Tiger II plates. Samples showed less than 0.1% molybdenum compared to 0.4 to 0.6% in earlier German armor. Manganese content had increased to compensate for missing alloying elements, but manganese alone could not replicate the properties of proper armor steel. Chemical analysis revealed the extent of material degradation. Soviet metallurgists compared Tiger II armor composition to specifications for standard armor steel. The deficiencies were systematic and severe. Without adequate nickel, the armor became brittle at low temperatures, exactly the conditions prevailing across the Eastern Front during winter operations. Without sufficient molybdenum, the steel lost strength under sustained high temperatures, precisely the conditions created by repeated shell impacts. The substitution of manganese for superior alloying elements produced armor that met thickness specifications, but failed to provide equivalent protection. These material deficiencies did not occur by accident. Germany had lost access to critical raw materials as Allied advances constricted territory under German control. Norwegian nickel production, captured early in the war, fell to Allied bombing in 1943 when RAF Bomber Command destroyed the Knaben molybdenum mine. Swedish iron ore shipments, essential to German steel production, declined throughout 1944 as Allied naval pressure increased. Finnish nickel mines at Petsamo fell to Soviet forces in October 1944, eliminating another critical source. By late 1944, Germany was attempting to produce armor steel without the materials that made armor steel effective. But the material quality problems paled beside what Soviet engineers discovered when they examined the welds. Welding represented perhaps the most critical aspect of armored vehicle construction. Properly executed welds created joints stronger than the surrounding plate. The weld bead, if correctly formed with appropriate filler material and proper heat treatment, should exhibit strength exceeding the base metal. German welding quality through 1943 had exemplified this standard. Soviet engineers examining early war German vehicles consistently noted weld quality as exceptional. Joints showed uniform penetration, minimal slag inclusion, proper heat-affected zones, and strength characteristics matching or exceeding specifications. The Tiger II welds told a different story entirely. Svirin's team began systematic examination of welded joints throughout the vehicle. They focused particularly on critical structural welds, the joints connecting hull plates, turret ring attachment points, suspension mounting brackets, areas where weld failure would cause catastrophic structural compromise. Visual inspection revealed problems immediately. Weld beads showed irregular profiles, inconsistent width, variable penetration depth. Some welds exhibited excessive undercutting, where the arc had melted too much base metal, creating stress concentrations. Other welds showed insufficient penetration, failing to achieve full thickness fusion. Soviet welding specialists performed destructive testing on sample sections cut from non-critical areas. They prepared metallographic samples, polished cross-sections of welds to mirror finish, etched them with chemical reagents to reveal microstructure, examined them under microscopes at magnifications up to 500 times. What they saw confirmed their worst suspicions. The weld microstructure showed characteristics of rushed execution and inadequate quality control. Slag inclusions appeared throughout many welds, trapped foreign material that created weakness and stress concentration points. Porosity, tiny voids formed by trapped gases during solidification, riddled some weld beads. Incomplete fusion zones showed where molten filler metal had failed to properly bond with base metal. The heat-affected zones, regions of base metal altered by welding heat, showed evidence of improper thermal cycles. Some areas had been heated too rapidly, creating brittle martensitic structures prone to cracking. Other areas had cooled too slowly, producing coarse-grained structures with reduced strength. The overall pattern suggested welders working under impossible time pressure, lacking proper materials, operating with inadequate supervision and quality control. Soviet engineers documented their findings with characteristic thoroughness. The technical report, filed with the main Auto-Armored Directorate in March 1945, contained detailed metallographic photographs, chemical analysis results, mechanical property measurements, and comparative data from earlier German vehicles. The conclusion was unambiguous. The quality of welding on late production Tiger II tanks is significantly worse than comparable German designs from earlier production periods. Multiple welds exhibit defects that would be considered unacceptable under Soviet military acceptance standards. This phrasing, carefully chosen by Soviet military bureaucrats, carried devastating implications. Soviet armored vehicle production operated under notoriously strict quality requirements. Stalin personally intervened multiple times to ensure armor quality met specifications. Factory directors faced criminal charges for delivering substandard vehicles. Welders whose work failed inspection could be reassigned to penal battalions. For Soviet engineers to declare German welding quality inferior to Soviet standards represented an extraordinary reversal of established understanding about German engineering superiority. The testing continued beyond metallurgical examination into functional evaluation. Soviet drivers operated the captured Tiger II across Kubinka's test courses. They measured maximum speed, acceleration, fuel consumption, turning radius, obstacle crossing capability. The Maybach HL 230P30 engine, producing 700 metric horsepower, moved the 69.8-ton vehicle adequately under ideal conditions. Maximum road speed reached 41.5 kilometers per hour during testing, slightly below the specified 45 kilometers per hour, likely due to worn components and improper maintenance during its final German operations. But sustained operations revealed the fundamental mismatch between engine output and vehicle weight. The power-to-weight ratio of approximately 10 horsepower per ton proved barely adequate for tactical maneuvering. Climbing a 15-degree slope required maximum engine output, causing temperatures to climb dangerously high within minutes. Cross-country movement at speeds exceeding 20 kilometers per hour generated mechanical stress that Soviet engineers calculated would cause component failures after relatively short distances. The cooling system, adequate for the 45-ton Panther, struggled desperately to dissipate heat generated by an engine operating continuously at high output to move 70 tons. Fuel consumption measurements shocked even Soviet engineers, accustomed to the prodigious fuel requirements of their own heavy tanks. The Tiger II consumed approximately 3 liters per kilometer during road movement, meaning the 860-liter fuel capacity provided approximately 280 kilometers maximum range under ideal conditions. Cross-country movement increased consumption to nearly 5 liters per kilometer, reducing operational range to less than 170 kilometers. Combat operations, with frequent acceleration, deceleration, turning, and high-power maneuvering, could exhaust fuel supplies in less than 100 kilometers. Soviet logistics officers calculated the implications. A Tiger II company of 14 tanks required approximately 42,000 liters of fuel for a 100-kilometer road march, assuming all vehicles completed the movement, without mechanical failure. This equaled the fuel requirement for an entire Soviet tank battalion equipped with T-3485 medium tanks. A Tiger II battalion of 45 tanks consumed fuel equivalent to 3 Soviet tank battalions. In the context of Germany's catastrophic fuel shortages by late 1944, these requirements were simply unsustainable. German forces increasingly lacked fuel not just for offensive operations, but for basic defensive repositioning. The transmission examination revealed additional evidence of compromised manufacturing quality. The Maybach Ulvar B transmission, designated OG 401216B, theoretically provided 8 forward gears and 4 reverse gears through a sophisticated hydraulic control system. Soviet engineers disassembled the transmission completely, examining every gear, bearing, seal, and shaft. The design itself impressed them. German engineers had created an extraordinarily sophisticated mechanism that provided smooth shifts and precise control when functioning properly. But manufacturing quality failed to match design sophistication. Gear teeth showed inconsistent hardening patterns. Surface hardness measurements varied by more than 15 Rockwell C points across individual gears, indicating inadequate quality control during heat treatment. Some gear teeth exhibited surface decarburization, loss of surface carbon content during heat treatment that reduced wear resistance. Bearing races showed scoring and spalling, evidence of contaminated lubricant or inadequate initial finish quality. Seals leaked, allowing oil to escape and contaminants to enter, accelerating wear throughout the transmission. Soviet engineers compared the Tiger II transmission to a Panther transmission captured in 1943. The differences were striking and systematic. The earlier Panther transmission showed uniform heat treatment, consistent surface finish, tight manufacturing tolerances. The Tiger II transmission showed variable heat treatment, rougher surface finishes, looser tolerances. Both transmissions used essentially the same design. The degradation in manufacturing quality could not be attributed to design changes. This was purely a manufacturing and quality control failure. The final drive examination provided perhaps the most damning evidence of manufacturing quality collapse. The final drive, connecting transmission output to drive sprockets, transferred enormous torque to move 70 tons. This represented one of the highest stress components in the entire drivetrain. French Army testing of captured Panthers in 1946 had identified final drive failure as the single most common mechanical problem, with average life expectancy of only 150 kilometers. Soviet engineers expected Tiger II final drives to exhibit similar weaknesses, given the even greater weight and stress. Disassembly revealed problems exceeding Soviet expectations. The final drive gears showed evidence of inadequate material quality and poor manufacturing practice. Gear tooth profiles deviated from specifications, indicating worn or improperly maintained production tooling. Surface hardness measurements revealed incomplete case hardening, where only the outer surface is hardened while maintaining a tough core. Some gear teeth showed hardness barely exceeding the core material, providing minimal wear resistance. The hardening patterns suggested rushed heat treatment with inadequate temperature control and quenching procedures. More troubling still, Soviet metallurgists found evidence of material substitution in final drive components. Specifications called for nickel-chromium steel, with specific composition providing optimal combination of strength and toughness. Chemical analysis of actual components showed substitution of cheaper steel with lower alloy content. Without adequate nickel and chromium, the steel could not achieve specified strength even with proper heat treatment. German manufacturers, facing critical shortages of alloying elements, had apparently substituted inferior materials while maintaining external dimensions and hoping strength would prove adequate. The Soviet report documented systematically how these compromises compounded. Inadequate alloying elements reduced material strength, improper heat treatment further reduced strength. Worn tooling created dimensional inaccuracies that increased stress concentrations. Loose tolerances allowed misalignment that generated additional loads. Each individual deficiency might have been tolerable. The combination created a cascade of failures waiting to happen. Soviet engineers calculated that Tiger II final drives manufactured in late 1944 and early 1945 would likely fail after 100 to 200 kilometers of operation, possibly less under combat conditions involving frequent maneuvering. These findings fundamentally altered Soviet intelligence assessments of German industrial capacity. Throughout 1943 and early 1944, Soviet military intelligence had consistently warned that German technical superiority, particularly in armor quality and manufacturing precision, posed serious threats to Soviet forces despite growing numerical advantages. Captured German vehicles from this period supported these assessments. Panthers captured at Kursk showed excellent manufacturing quality. Tiger is captured at Leningrad demonstrated meticulous attention to detail. Even late-model Panzer IVs exhibited quality workmanship. The Tiger II examination revealed that this German advantage had evaporated by late 1944. The combination of material shortages, skilled labor depletion, Allied bombing disruption, and impossible production demands had broken German quality control systems. Factories were producing vehicles that met dimensional specifications but failed to provide design-level performance. Armor reached specified thickness but lacked proper composition. Welds appeared complete but contained internal defects. Drivetrains fit together but used substandard materials with inadequate heat treatment. Soviet intelligence officers recognized the strategic implications immediately. A German armored force equipped with vehicles suffering systematic quality problems would experience operational availability rates far below nominal strength. Tanks would break down during movement to contact before engaging enemy forces. Vehicles that reached the battlefield would suffer accelerated component wear, requiring more frequent maintenance with longer repair times. Units would be forced to cannibalize broken vehicles for spare parts, further reducing operational strength. The cumulative effect would be German armored forces unable to sustain operations at the tempo required for successful offensive action or even effective mobile defense. This understanding shaped Soviet operational planning for the final campaigns of the war. Soviet commanders increasingly accepted casualties from frontal assaults, calculating that German mechanical attrition would prevent effective exploitation even if initial defenses held. Soviet logistics officers allocated fewer resources to anti-tank weapons, recognizing that German armor would likely break down faster than it could be destroyed in combat. Soviet tank designers reduced emphasis on heavy armor protection, understanding that German heavy tanks would rarely be present in operational quantities due to mechanical unreliability. The human dimension of German manufacturing collapse emerged from interrogation of captured German tank crews. Prisoners taken during January 1945 offensives across Poland and East Prussia provided remarkably consistent accounts of Tiger II reliability problems. Drivers reported transmissions failing after short movements. Commanders described engines overheating during routine operations. Maintenance personnel recounted impossible repair, demands with inadequate tools, missing spare parts, and untrained assistants. One particularly detailed account came from Feldwebel Ernst Bachmann, a Tiger II driver captured near Kielce in January 1945. Bachmann had received his Tiger II in November 1944, one of the last vehicles delivered to his unit before Soviet offensives disrupted German supply lines. He described the vehicle's progressive deterioration with painful precision. The transmission had developed problems within the first 50 kilometers, requiring adjustment of shift mechanisms. By 100 kilometers, second gear became unreliable, grinding during shifts despite proper clutch operation. At 150 kilometers, the cooling system developed a leak that maintenance personnel could not fully repair, requiring constant monitoring and periodic water additions. Bachmann's final drive failed completely at approximately 180 kilometers during a tactical repositioning movement. He described hearing unusual noises from the right side drive mechanism, reducing speed, then feeling the entire drivetrain seize. His Tiger II coasted to a stop on a rural Polish road. The final drive housing had cracked, spilling lubricant and allowing gear teeth to destroy themselves within minutes. Recovery was impossible. Soviet forces were advancing too rapidly. His crew placed demolition charges and withdrew on foot, abandoning their nearly new Tiger II to enemy capture. This pattern repeated across multiple prisoner accounts. Soviet interrogators compiled testimonies from dozens of German tank crews, creating a composite picture of systematic mechanical failure. Tigers IIs delivered in late 1944 averaged less than 200 kilometers before requiring major repairs. Some failed even faster. Units reported that approximately 30 to 40% of Tigers IIs were non-operational at any given time, not from combat damage but from mechanical failures awaiting parts and repairs that rarely came. If you could find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The production circumstances that created these failures emerged from captured German industrial documentation. Allied bombers had struck the Henschel factory in Kassel repeatedly throughout 1944. Major raids occurred in March, September, and October, each causing weeks of production delays. By November 1944, monthly Tiger II production had fallen from peaks of nearly 100 units in summer 1944 to fewer than 30 units. The factory operated with approximately 60% of required skilled workers. Allied bombing and Eastern Front demands had drained available labor. Replacements came increasingly from forced labor camps, prisoners of war, concentration camp inmates, workers who possessed minimal training and no commitment to quality control systems that had maintained standards through 1943 collapsed under these pressures. Inspectors who would have rejected substandard welds were reassigned to combat units. Testing procedures that would have identified weak components were abbreviated or eliminated to meet production quotas. Specifications requiring specific materials were quietly modified to allow substitutions when proper materials were unavailable. The cumulative effect transformed German manufacturing from a system producing sophisticated, reliable equipment into a system producing sophisticated-looking equipment that functioned poorly. Soviet engineers at Kubinka understood these realities with cold clarity. Their detailed technical reports documented not just what had gone wrong with Tiger II manufacturing, but why it had gone wrong and what it meant strategically. The conclusions shaped Soviet military thinking for decades. Quality could not be separated from industrial capacity, skilled labor availability, and supply chain integrity. The most sophisticated design produced with inadequate resources became a liability rather than an asset. Reliable, adequate equipment defeated unreliable, superior equipment in sustained operations. The broader pattern of German industrial degradation extended beyond armor production into virtually every category of military equipment. Soviet technical intelligence teams examining captured German small arms, artillery, vehicles, and aircraft throughout 1945 consistently documented similar quality deterioration. The MG-42 machine gun, legendary for reliability through 1943, showed increased failure rates in late-war production due to material substitutions and relaxed tolerances. The 88mm anti-aircraft gun, feared throughout the war for accuracy and effectiveness, exhibited barrel wear problems in final year production from inferior steel alloys. Even the Kar-98K rifle, Germany's standard infantry weapon since the 1932nd, showed quality decline in 1945 production with rough finishes and loose-fitting parts. This systematic manufacturing collapse reflected fundamental contradictions in German war strategy. Adolf Hitler personally demanded increased production of advanced weapons, while Allied bombing systematically destroyed the industrial infrastructure needed to produce them. He insisted on sophisticated designs, incorporating the latest technology, while material shortages made proper production impossible. He ordered accelerated production schedules, while skilled workers were conscripted for increasingly desperate military operations. These contradictory demands created impossible situations for German industrial managers who faced criminal prosecution for failing to meet production quotas regardless of circumstances. The Henschel factory situation illustrated these contradictions with brutal clarity. Albert Speer, Reich Minister of Armaments and War Production, visited Kassel in October 1944 to demand increased Tiger II output. He required minimum 50 tanks per month, despite recent bombing that had destroyed 3 production halls and killed hundreds of skilled workers. Factory managers explained that meeting these quotas with available resources required compromising quality standards. Speer reportedly responded that quantity mattered more than perfection, that adequate tanks delivered rapidly were more valuable than perfect tanks delivered slowly. This prioritization of quantity over quality represented a complete reversal of traditional German manufacturing philosophy. Prussian military tradition emphasized technical excellence, precision craftsmanship, and meticulous attention to detail. German engineering culture valued sophisticated solutions to complex problems, producing weapons that impressed even enemies with their technical sophistication. This approach had served Germany well in earlier wars, where conflicts were decided by relatively small professional armies fighting, campaigns of limited duration. World War II was not that kind of war. By late 1944, Germany faced a war of industrial attrition against opponents whose combined industrial capacity exceeded German output by factors of 5 to 10 in most categories. The Soviet Union alone outproduced Germany in tanks, artillery, and aircraft. Adding American and British production created overwhelming material superiority that no amount of German technical sophistication could overcome. Germany needed vast quantities of reliable equipment that could be produced despite material shortages and operated despite limited fuel. Instead, German industry produced sophisticated equipment in inadequate quantities that consumed scarce resources and broke down frequently. The Tiger II exemplified this strategic failure perfectly. Each Tiger II consumed resources equivalent to approximately 3 Panzer IV medium tanks or 5 Stug 3 assault guns. The Tiger II required specialized production, facilities, highly skilled workers, and materials that were increasingly unavailable. The Panzer IV and Stug III could be produced in existing facilities by semi-skilled workers using readily available materials. The Tiger II needed extensive maintenance, frequent repairs, and specialized spare parts. The Panzer IV and Stug III required modest maintenance and used common components. The Tiger II consumed fuel at ruinous rates. The Panzer IV and Stug III had acceptable fuel efficiency. Soviet officers conducting strategic analysis calculated the implications with mathematical precision. Germany produced approximately 490 Tiger IIs during the entire war, with peak monthly production never exceeding 100 units. That same industrial capacity, if dedicated to Panzer IV production, could have produced approximately 1,500 tanks. If dedicated to Stug III production, approximately 2,500 assault guns. The operational effectiveness of 1,500 reliable Panzer IVs or 2,500 reliable Stug ATIEs would have exceeded 490 unreliable Tiger IIs by substantial margins. The Tiger IIs spent more time awaiting maintenance than engaging enemies. The Panzer IVs and Stug IS would have been present and operational when needed. This conclusion was not speculation, but mathematical certainty derived from documented operational availability rates. German records compiled after the war showed Tiger II operational readiness averaging approximately 50 to 60% throughout 1945. This meant that a Tiger II battalion nominally equipped with 45 tanks could expect perhaps 25 to 30 actually operational on any given day. The remaining 15 to 20 tanks were undergoing maintenance, awaiting spare parts, or disabled awaiting recovery. By comparison, Panzer IV operational readiness in the same period averaged approximately 70%, and Stug III exceeded 75%. The reliability differential compounded the numerical disadvantage, creating battlefield situations where German forces were outnumbered by even larger margins than production statistics suggested. The Soviet testing of captured Tiger IIs continued throughout spring 1945 as additional vehicles were recovered from battlefields across Eastern Europe. Each examination confirmed the initial findings. Late production Tiger IIs suffered from systematic quality problems, affecting virtually every component. Engineers at Kubinka compiled comparative data from multiple vehicles, documenting the progression of quality decline. Tiger IIs produced in early 1944 showed relatively good manufacturing quality, comparable to earlier German vehicles. Tiger IIs produced in mid-1944 showed initial signs of material substitution and relaxed quality control. Tiger IIs produced in late 1944 and early 1945 exhibited severe quality problems across all systems. One particularly revealing comparison involved examining welds on Tiger II turrets from different production periods. A turret manufactured in February 1944 showed weld quality that Soviet engineers rated as excellent by any standard. Uniform bead profiles, consistent penetration, minimal defects, proper heat treatment. Metallurgic examination revealed welds that matched or exceeded base metal strength. A turret manufactured in November 1944 showed noticeably degraded quality. Irregular bead profiles, variable penetration, increased defects, questionable heat treatment. Metallurgic examination revealed welds approximately 80% of base metal strength. A turret manufactured in January 1945 showed quality that Soviet engineers characterized as barely acceptable. Extremely irregular beads, inconsistent penetration, numerous defects, inadequate heat treatment. Metallurgic examination revealed welds achieving only 60 to 70% of base metal strength. This progressive degradation reflected the systematic collapse of German industrial capacity under combined pressure of Allied strategic bombing, material shortages, and labor depletion. The Henschel factory had employed approximately 8,000 workers in early 1944, including roughly 2,000 skilled welders, machinists, and assembly specialists. By November 1944, total employment had declined to approximately 5,000, with skilled workers reduced to fewer than 800. The gap was filled with forced laborers from occupied territories and concentration camps, workers who possessed minimal technical training and worked under guard with no incentive for quality. German welding specialists who survived the war and were interrogated by Allied intelligence officers provided devastating accounts of production conditions during the final months. One master welder from the Henschel factory, Wilhelm Müller, described the situation in a 1946 interview with American technical intelligence officers. He had worked at Kassel since 1938, training apprentice welders and supervising quality control. By late 1944, he reported, quality control had become essentially impossible. Welders worked 12-hour shifts 7 days per week under impossible pressure to meet production quotas. Many welders were recent trainees, with only weeks of instruction rather than the years of apprenticeship traditionally required. Welding rod quality had declined as material shortages forced substitution of inferior filler metals. Müller described watching Tiger II hulls move through production with welds that would have been rejected automatically just 1 year earlier. He protested to supervisors, documenting specific defects and predicting field failures. His concerns were dismissed. Production quotas took absolute priority. Müller eventually stopped protesting, understanding that his objections would change nothing except possibly resulting in his own reassignment to a punishment battalion. He continued, supervising production of tanks he knew were defective, knowing they would fail in service, knowing German soldiers would die because of manufacturing shortcuts taken to meet impossible demands. This moral dimension of German manufacturing collapse extended throughout the industrial system. Engineers who understood the consequences of material substitutions were ordered to approve them anyway. Inspectors who identified defective components were told to pass them for assembly. Factory managers who warned about quality problems were threatened with criminal prosecution for defeatism. The entire system operated under a combination of denial, desperation, and terror that prevented rational decision-making about industrial capacity and realistic capabilities. The Soviet intelligence assessment compiled from Tiger II, testing and broader industrial analysis reached Stalin's desk in April 1945. The report concluded that German armoured vehicle production had collapsed not just quantitatively but qualitatively. Germany was producing fewer tanks than in previous years, and the tanks being produced were significantly inferior to earlier production. The combination meant that German armoured forces were declining in capability even faster than simple production statistics suggested. Soviet operational planners could assume that German tank units would be weaker, less mobile, and less sustainable than unit designations implied. This intelligence shaped the final Soviet offensives into Germany during April and May 1945. Soviet commanders accepted higher casualties from frontal assaults, calculating that German mechanical attrition would prevent effective counterattacks even if initial defenses held. Soviet logistics officers allocated resources toward maintaining Soviet offensive momentum rather than preparing for potential German armoured counteroffensives that intelligence assessments indicated were increasingly unlikely. Soviet tank production. Priorities shifted toward maintaining numerical superiority rather than matching German technical sophistication, understanding that reliability and quantity would prove decisive. The American experience with captured Tiger IIs paralleled Soviet findings, though with less systematic testing. American forces encountered Tiger IIs primarily during the Battle of the Bulge in December 1944 and subsequent operations in Germany during early 1945. American intelligence teams recovered several Tiger IIs in various conditions, most abandoned due to mechanical failure or fuel exhaustion rather than combat damage. The most thoroughly examined American-captured Tiger II, chassis number 332, underwent detailed evaluation at Aberdeen Proving Ground in Maryland. American engineers reached conclusions nearly identical to Soviet assessments. The Tiger II represented impressive design, compromised by inadequate execution. The armor was thick but improperly composed. The gun was powerful but mounted in an unreliable platform. The drivetrain was sophisticated but manufactured with substandard materials and quality control. American technical reports noted specifically that weld quality appeared inferior to earlier German vehicles examined during 1943. Metallurgical analysis confirmed material composition problems, particularly nickel and molybdenum deficiencies, that reduced armor effectiveness despite meeting thickness specifications. American tactical intelligence bulletins distributed to frontline units incorporated these findings into engagement recommendations. Intelligence Bulletin 185, issued in October 1944, advised tank commanders that Tiger IIs were dangerous in direct combat but vulnerable to mobility warfare that forced movement and maneuvering. The bulletin specifically noted that Tiger IIs frequently broke down during sustained operations, suggesting tactics that forced German armor to relocate repeatedly rather than engaging from prepared positions. American tank commanders learned to bypass Tiger IIs when possible, allowing them to remain stationary while American forces maneuvered around them, calculating correctly that mechanical problems would eventually force abandonment. The broader lessons from Tiger II manufacturing quality collapse extended far beyond World War II into post-war military-industrial planning. American defense officials studying German industrial failure identified several critical principles that shaped subsequent procurement policy. First, sophisticated design without adequate production capacity created liabilities rather than assets. Second, quality control could not be maintained under impossible production pressure with inadequate resources. Third, material substitutions had cascading consequences that undermined overall system performance. Fourth, reliability mattered more than raw specifications in determining operational effectiveness. These principles directly influenced American tank development throughout the Cold War. The M48 Patton tank, entering service in 1952, emphasized mechanical reliability and ease of maintenance as primary design requirements equal to armor protection and firepower. Development specifications explicitly required that the tank be producible in existing facilities using readily available materials without exotic alloys that might become unavailable during wartime. Quality control procedures included extensive durability testing before production approval, directly addressing the rushed development that had plagued German vehicles. The M60 tank, entering service in 1960, continued this emphasis with additional requirements for component commonality and simplified maintenance procedures. Design specifications mandated that major components like engine and transmission be removable and replaceable by unit-level maintenance personnel using standard tools. This directly addressed German experience where specialized equipment and factory-level expertise were required for major repairs, limiting field maintainability. The requirement reflected lessons learned from examining German vehicles that were technically sophisticated but practically unmaintainable under field conditions. The M1 Abrams tank, entering service in 1980, represented the culmination of this philosophy. Despite incorporating revolutionary technologies including composite armor and a gas turbine engine, the Abrams was designed from inception with reliability and maintainability as co-equal requirements with combat performance. The turbine engine, despite initial skepticism, proved remarkably reliable with far fewer moving parts than conventional diesel engines. The transmission, though sophisticated, was designed for removal and replacement in under 4 hours, using standard maintenance equipment. These requirements reflected institutional memory of German over-engineering lessons purchased at considerable cost during World War II. Soviet tank development followed parallel evolution, informed by the same lessons. The T-54 medium tank, entering production in 1947, emphasized simplicity and reliability over technical sophistication. The design used conventional materials, readily available from Soviet industrial capacity, without exotic alloys, requiring difficult procurement. Manufacturing procedures stressed quality control with extensive testing before acceptance. These priorities reflected direct Soviet experience testing captured German vehicles and understanding how manufacturing shortcuts compromised operational effectiveness. The T-62 tank, entering service in 1961, continued Soviet emphasis on producibility and reliability. Design specifications explicitly rejected sophisticated features that would complicate production or reduce reliability. The tank used a relatively simple main gun without elaborate stabilization systems. The engine, was an evolution of proven designs rather than revolutionary technology. The transmission was mechanically simple, with fewer potential failure points. Soviet military doctrine emphasized that tanks must be present and operational when needed, that sophisticated capabilities provided no advantage if vehicles were disabled awaiting maintenance. The institutional memory of German manufacturing quality collapse influenced not just tank design, but broader military procurement philosophy throughout the post-war period. American and Soviet military planners both recognized that industrial capacity, material availability, and production quality determined military effectiveness as much as individual weapon specifications. This understanding shaped procurement decisions, industrial policy, and strategic planning for decades. The human cost of German manufacturing failures extended beyond tactical defeats into strategic consequences that shaped the war's conclusion. German soldiers fighting in Tiger IIs that broke down repeatedly learned through bitter experience that their supposedly superior equipment was unreliable. This knowledge undermined morale and created resignation that no amount of technical sophistication could overcome Allied material superiority. German tank crews became cautious, hesitant to commit their unreliable vehicles to aggressive action that German doctrine required, knowing mechanical failure was more likely than enemy destruction. Soviet soldiers who captured intact Tiger IIs and examined their construction gained confidence from understanding German vulnerabilities. They learned that German technical reputation exceeded reality, that propaganda about superior Aryan engineering was exactly that, propaganda unsupported by material evidence. This knowledge spread through Red Army units, reducing the psychological impact of encountering German heavy armor. Soviet tank crews became more willing to engage Tiger IIs aggressively, understanding that mechanical problems likely degraded German combat effectiveness. The final accounting of Tiger II production and deployment revealed the magnitude of Germany's strategic error. Approximately 490 Tiger IIs were produced between January 1944 and March 1945. Of these, perhaps 200 were actually deployed to combat units and saw action. The remainder were destroyed during production by Allied bombing, disabled during transit by mechanical failure, or captured before reaching the front lines. Of the 200 that reached combat, Soviet and American records suggest that fewer than half were actually destroyed by enemy fire. The majority were abandoned due to mechanical failure, fuel exhaustion, or lack of recovery capability. This represented one of the least effective uses of scarce German industrial resources during the entire war. Each Tiger II consumed materials and labor that could have produced multiple, more reliable vehicles. Each Tiger II required logistics, support that exceeded German capacity to provide. Each Tiger II tied down maintenance personnel and resources desperately needed elsewhere. The program diverted resources from more practical weapons that might have extended German resistance, consuming scarce nickel, chromium, molybdenum, and skilled labor for minimal operational return. Soviet post-war analysis calculated that if Germany had allocated Tiger II resources to producing additional Panzer IVs and Stug IIIs, German armored strength in 1944 and 1945 could have been 20 to 30% higher with dramatically better operational availability. This would not have changed the war's outcome, given overwhelming Allied advantages in industrial capacity and manpower, but it would have made Soviet operations more costly and potentially delayed Germany's defeat by several months. Instead, German leadership's fixation on technical sophistication over practical reliability accelerated their defeat. The Tiger I-2 today serves as a permanent reminder in military museums and military education programs about the relationship between engineering, ambition, and manufacturing reality. The handful of surviving Tiger IIs, displayed at Kubinka, Aberdeen, Fort Benning, and several European museums, impress visitors with their massive size and thick armor. Museum plaques describe the powerful gun and sophisticated design. But informed observers understand that these machines represented Germany's industrial death spiral made manifest in steel. Engineering students studying manufacturing quality control examine Tiger II production as a case study in how quality systems collapse under impossible pressure. They learn about the cascading consequences of material substitutions, the importance of maintaining skilled workforce, the relationship between production, pressure, and defect rates. Business school students analyze the Tiger II program as an example of strategic misalignment between objectives, capabilities. They examine how organizational culture can drive decisions that undermine stated goals, how denial and wishful thinking can substitute for rational planning. Military officers studying logistics and sustainability examine Tiger II operational history to understand how reliability determines effectiveness more than specifications. They calculate availability rates, maintenance requirements, and logistics footprints to understand why sophisticated equipment that cannot be sustained proves less valuable than adequate equipment that can. These lessons remain relevant to contemporary military procurement, where technological sophistication must be balanced against reliability, maintainability, and industrial capacity. The Soviet technical reports from Kubinka Proving Ground testing, declassified decades after the war, provide the most detailed documentation available of German manufacturing quality decline during the war's final year. Soviet engineers approached the examination with systematic rigor that produced remarkably thorough analysis. Their findings, initially classified and shared only with senior Soviet military leadership, eventually entered military education curricula and influenced Soviet industrial planning. The reports served as cautionary tales about the consequences of sacrificing quality for quantity, about the importance of maintaining skilled workforce, about the relationship between material availability and manufacturing capability. The welding quality problems documented so thoroughly by Soviet metallurgists became particularly significant in post-war analysis. Welding represented a manufacturing process where quality depended critically on worker skill, proper materials, adequate time, and effective supervision. Cutting corners in any of these areas produced immediate degradation in weld quality, with predictable consequences for structural integrity. The Tiger II welds examined at Kubinka showed how systematically these factors had deteriorated in German industry by late 1944. The broader pattern extended beyond German experience into universal lessons about industrial warfare. Modern military conflicts require sustained industrial production over extended periods. Initial equipment stocks matter less than the capacity to replace losses and maintain operational readiness. Quality cannot be separated from production context, including available materials, skilled labor, and time pressure. Sophisticated designs require sophisticated production capability that may not survive wartime disruption. Reliability determines operational effectiveness more than raw performance specifications. These truths, documented through systematic examination of German manufacturing failures, shaped military thinking throughout the post-war period and continue influencing defense planning into the present day. The Tiger II, magnificent in specifications and impressive in appearance, failed because German industry, by late 1944, could not produce what German engineers had designed. The gap between design intent and manufacturing reality doomed the program to ineffectiveness, regardless of how thick the armor was or how powerful the gun was. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.